In this lecture, we will start a new topic, that is single-phase induction motor. In our previous lectures, we discussed the operation of three-phase induction motors only. The three-phase induction motors are supplied by three-phase power system, and these types of motors are the most common ones in larger commercial and industrial settings. However, most homes and small businesses do not have three-phase power available. For example, at our household, we do not have three-phase power supply. Generally, three-phase power supplies are given to the commercial and industrial areas, and a special permission is needed to be taken from the government. So, for residential areas where we do not have three-phase power available, all motors must run from single-phase power sources. And that type of AC machines will be discussed in this lecture, and that will be supplied by single phase AC supply. That's why it is called single phase induction motor. The major problem associated with the design of single phase induction motor is that, unlike three phase power sources, a single phase source does not produce a rotating magnetic field. As we saw earlier, if we have a certain mechanical configuration, by employing three-phase power source, we can have rotating magnetic field. So in single-phase power supply, we have one phase and another neutral. This is phase connection, this is neutral connection. And supply is coming from the source. Now, if we have a configuration like this, and we give the phase connection here, and another side is connected with neutral. This is phase connection, this is neutral connection. So there will be a creation of magnetic field. That magnetic field will be alternating as the supply is alternating. So we know from single phase source we have this type of supply voltage. So when the voltage, this is voltage, this is time. When the voltage is 0, it's better to write omega t. When the voltage is 0, the field, magnetic field produced here will be 0. When it goes to the positive direction and attains the maximum value, so it will have the highest magnitude of magnetic field, which means we have north here, south here. Again, the magnitude of voltage will be decreased, so the current flowing will be decreased accordingly, and current will be lagging. So when the current becomes 0 here, again field will be 0 here. Again, when it changes its direction and goes to the opposite direction, it will have the magnetic field strength in the opposite direction. So in this way, we'll have a pulsating magnetic field. Instead of getting rotating magnetic field, we'll have a magnetic field that will start from 0, go up, go up, go up, and attains the maximum value and comes back to 0 position, changes its direction and go up in the opposite direction and comes to the 0 position. So in this way, the magnetic field will have a pulsating in nature. Since there is no net rotating magnetic field, conventional induction motors cannot function and special designs are necessary. First of all, let us discuss on a very special feature of this type of motor. That is, if you provide a single phase supply with this configuration, then what will happen? There will be creation of pulsating magnetic field as we discussed here. If we place a squirrel cage type of rotor, you know what is squirrel cage type rotors? We already discussed in our three-phase induction motor lectures. We have squirrel cage rotors. This is the side view and this is the end rings, and there are birds connected with two end rings. Here there will be a creation of pulsating magnetic field, not rotating magnetic field. So there will be no relative speed between the rotating magnetic field and the rotors. and it is understood that rotor won't be able to rotate. But there is an interesting feature. If we provide an external force in any direction, for example, we are providing an external force to the rotor in anti-clockwise direction, the rotor will start rotating in that direction. Again, if we provide an external force in clockwise direction after giving this supply, at the very beginning motor will not start, but if we provide this external force, motor will start rotating in that direction. If we provide the external force in the anti-clockwise direction, motor will start rotating in the anti-clockwise direction. If we provide an external force to the clockwise direction, then the motor will start rotating in the clockwise direction. This strange behavior of single-phase induction motor can be explained on the basis of double field revolving theory. So we'll discuss double field revolving theory. Before starting the theory, let me tell you again what happens here. When we give a single phase supply through this line, there is a creation of pulsating magnetic field and the rotor does not get any starting torque. However, if we give an external force in any direction, the rotor starts rotating in that direction. The double field revolving theory is proposed to explain this dilemma of no torque at start and the produced torque when the rotor starts rotating by means of external force. Suppose the produced flux due to this current I1 is represented by phi. So phi will be alternating magnetic flux as I1 is alternating current. So this phi can be represented by this equation, phi equal to phi m cos omega t. Phi m is the maximum amplitude. So if we have sinusoidal shape current, though it's voltage, but the same shape can be obtained for the current case, though that current will be 90-degree lagging as it is almost purely inductive. So this phi will also have same sinusoidal shape, and phi m is the maximum amplitude of that sinusoidal shape. Now if I draw the vector here, we'll have phi in this direction. This is the maximum amplitude phi m, and suppose this is x axis and this is the y axis. Now let us consider two rotating magnetic fluxes. One is phi 1, another is phi 2. They are rotating in the opposite direction. Phi 2 is rotating in clockwise direction and phi 1 is rotating in the anti-clockwise direction. Suppose these two rotating magnetic field phi 1 and phi 2, both of them are having equal magnitude, that is phi m by 2, and rotating in the opposite direction with angular velocity omega. So their angular velocity will be omega. Hence this angle will be omega t and this angle will also be omega t. And the magnitude here we can say phi 1 equal to phi m by 2, phi 2 equal to phi m by 2. We are considering the half of this maximum magnitude here. The green magnetic field is rotating in the anti-clockwise direction and the red one is rotating in the clockwise direction with angular velocity omega. Now for each time step, phi 1 and phi 2 both will have x component and y component. For example, for phi 1, the x component will be phi 1 cos omega t and the y component will be phi 1 sin omega t. For phi 2, x component will be phi 2 cos omega t and y component will be phi 2 sin omega t. We can see the x component falls on the top of each other, but y components, they are in the opposite direction. So we can write total x component due to phi 1 and phi 2 equal to phi m by 2 cos omega t plus phi m by 2 cos omega t. The summation becomes phi m cos omega t. For the y component, we can write total y component equal to phi m by 2 sine omega t, as they're opposite to each other, so we need to put minus here, phi m by 2 sine omega t. Hence we'll get the value equal to 0. So the resultant flux can be written as phi equal to root over phi m cos omega t whole square plus 0 square. That will return us phi m cos omega t. So we can see the resultant flux vector phi is equal to phi m cos omega t along the x-axis. Therefore, an alternating field can be replaced by two rotating magnetic fields of its half amplitude rotating in the opposite direction at synchronous speed. We can say at any value of omega t, the summation of phi 1 and phi 2 will give us this phi m cos omega t. If we add these two values at omega t equal to 0, so omega t equal to 0 means phi 1 cos 0, cos 0 means 1. So we'll get phi 1 here and phi 2 here. Phi 1 equal to phi m by 2, phi 2 equal to phi m by 2. So at omega t equal to 0, we'll get the value phi m. And from this equation as well, when omega t equal to 0, we are getting phi equal to phi m. Now after some times, if phi 1 and phi 2 keeps rotating, this green color will come here and the red color will come here when omega t equal to 90 degree. We know for omega t equal to 90 degree, this phi value will become 0. And from these two rotating magnetic field, we can see we do not have any x component, only we have the y component, and they are opposite to each other. So they will be cancelled out, we'll get the 0. Again, if it continues rotating, we'll get this rotating magnetic field here and the red one here. So at that point, the summation will be in this direction. If we add this 2x component, we'll get the summation here in this direction. In this way, it will keep increasing, and when they will be on the top of each other, it will attain the maximum value. When they cross the lines, then it will start reducing. When the green color comes here and red color goes there, they will be opposite to each other. Eventually, the value will be 0. So we can say this phi can be represented, this pulsating phi can be represented by two rotating magnetic field which are rotating in the opposite direction, having the half of the magnitude of phi m. Now from this theory, we can say we have two rotating magnetic field. One is rotating in the anti-clockwise direction, another is rotating in the clockwise direction, and both are having the same amplitude and same speed. So both are pulling this rotor in opposite direction. That's why rotor can't start. Now consider the case that the rotor is stationary and the stator winding is connected to a single phase supply. The alternating magnetic flux that is produced by the stator can be presented as the sum of two rotating fluxes. One is phi 1 rotating in the anti-clockwise direction, another is phi 2 rotating in the clockwise direction. And this phi 1 and phi 2 both are having the amplitude that is half of the magnitude of the alternating magnetic field. And both the magnetic fields are rotating with synchronous speed. That means ns equal to 120 f over p. So if we consider this phi 1 flux only, that is rotating in the anti-clockwise direction, that will produce a torque tau 1 on this rotor. Again, if we consider this phi 2 flux only, that will also produce another torque tau 2, which will be exerted in the clockwise direction. At a standstill, these two torques are equal and opposite, and the net torque developed is 0. Things will be more clear if we draw the torque speed characteristics curve for two magnetic fields. Suppose in the x-axis we are taking the rotor speeds. If we consider this is nr, which is in the anti-clockwise direction, then nr negative will represent the clockwise direction rotation. This is nr minus nr, and this is tau value. Now for phi 1, the torque developed on this rotor will look like this, and for phi 2, the torque developed on this rotor will be opposite to this one, and that will look like this. If we extend the torque curve, it will be something like this. Now this torque is generated due to phi 1 rotation. This torque curve is generated due to phi 2 rotation. Here the value of nr equal to 0. That means rotor at standstill. Now what is the net torque exerted on this rotor? The summation of these two torque. At this point, this value and this value, though they are not scaled, but they are equal. So at this point, the net torque will be 0. So if we plot this curve, the net torque will look like this. So this is the net torque curve, net torque. If you have a configuration like this and give a supply, we can see at nr equal to 0, the torque produced by the motor, that means starting torque, is 0. That's why motor won't be able to start. But somehow if we provide a force in any direction, for example, we are providing a force in anti-clockwise direction, so the rotor will get some speed. When it gets some speed, it comes to this point which has a positive torque, and as that is in the unstable region, so it will keep moving and will come to a stable position based on the load connected with the rotor. So this will be the operating point. In this way, if we provide a force in any direction, that will come to this unstable region and it will follow this red line and come to a stable point. Again, if we provide a force in the clockwise direction, then it will come here and come to this point. So once it reaches to this point, it will start following this line as it has got a forward direction force, so it will keep moving in this direction and it will come to a stable position and it will keep running in that direction. In this way, we can say that when we give supply, motor won't be able to start, but if we can give a force to the rotor, motor will start rotating in that direction. So in nutshell, we can say after having this single phase supply, in this stator connections, if we place a squirrel cage rotor, the motor won't be able to start, but if we give a force in any direction, motor will start rotating in that direction, and which can be explained by this theory. The theory is based on two oppositely rotating magnetic field, namely phi 1 and phi 2, and both of them are pulling the rotor in their own direction, and at the very beginning their pulling force are same. That's why motor can't start, but if we provide a force in any direction, motor starts running in that direction. For this type of motors, every time you switch on the power supply, you'll have to give an external force in order to rotate the motor, which is not convenient to use. Again, if you mistakenly rotate in the opposite direction, the motor will start rotating in that direction, which may not be desired. So we need to make this motor self-starting. Motors with this configuration are not self-starting. So how to make the motor self-starting? Before we start that, we need to have a rotating magnetic field which should be rotating in one of the directions, not like this one. Phi 1, phi 2, they are rotating in the opposite direction with same magnitude, but we'll have to design our circuit in a way so that we can have one rotating magnetic field which will be dominating. In order to do that, what we can do, we can split the phase. We have single phase supply. From single phase, we need to make multiple number of phases. First of all, we'll try to create two phases from the single phase supply. That feature is called splitting the phases. Before I start that topic, let's see how a rotating magnetic field is created from a two-phase supply. Rotating magnetic field from a two-phase supply. Suppose by any mechanism, the single phase is splitted into two-phase supply. So if we have this type of mechanical configuration, these are the poles, stator poles. Suppose phase 1 is connected here. This is neutral. So this is phase 1 and another phase current. This is I1. Another phase current is connected here. This is neutral. This is I2. So there will be a creation of pulsating magnetic field in this direction and in this direction. So we'll have a magnetic field in x-axis direction and we'll have another magnetic field in y-axis direction. And the magnetic field that will be created in x-axis and y-axis both will be having sinusoidal in nature. The magnetic field that will be created that can be expressed by equation phi A equal to phi m sine omega t, and the magnetic field or magnetic flux that will be created in y-axis direction that can be represented by phi b, which is 90 degree apart from this current. We can say sine omega t plus 90 degrees. So in this direction we will have phi a, which will be pulsating with this equation, and in y-axis direction we'll have phi b, which will have pulsating in nature in y direction. Now let's see the cases for different omega t value as we did for three-phase induction motor case. When omega t equal to 0 degree, the value of phi a will be phi m sine 0, and we know sine 0 equal to 0, so this will be equal to 0, and the value of phi b equal to phi m sine omega t plus 90 degree, omega t equal to 0, that will eventually give us the value of sine 90 degree, which is equal to 1. So we are getting phi b equal to phi m. If we plot this version, then in this x-axis direction we have phi a, which is 0. In y-axis direction we have phi b, that is equal to phi m. So we'll have phi m in y-axis direction. Now let's see what happens when the value of omega t is equal to, for example, 45 degree. In that case, the value of phi a equal to phi m sine 45 degree, that returns us phi m over root 2, and the phi b equal to phi m sine 45 degree plus 90 degree, that is equal to 135 degree, which is also equal to phi m divided by root 2, or here it will be phi m by root 2. If we plot this version, in x-axis direction we have phi m by root 2, and in y-axis direction we have another phi m by root 2. So the resultant magnetic field will be in this direction, the summation of these two. So the resultant magnetic field phi r equal to root over phi m by root 2 square plus phi m by root 2 square. That will return us phi m. If we plot the same for other omega t value, we'll see that it will change its location, but it will have the maximum amplitude which is equal to phi m. In this way, for different cases, we can see for two-phase current supply, the resultant magnetic field will be a rotating magnetic field that will have a magnitude, constant magnitude of phi m. This theory will be utilized in order to make the single-phase induction motor self-starting. We will discuss that in the next lecture. Thank you.